Okay, maybe I'll get started. Last class, we looked at an example of a Monte Carlo simulation using random number generation. Today's class is also an example of Monte Carlo method and random number generation. In the last class, we looked at simulating radioactive decay chains. So that's a problem that you can solve analytically, but it gets complicated to solve analytically. And it's very straightforward to solve it numerically with Monte Carlo method. So it was a powerful approach for the Monte Carlo method. Today's class, I want to talk about another problem. It's the problem of random walks or random walk processes related to diffusion processes. This is also a problem that in some cases you can solve analytically, and we'll look at an analytical solution of it. But again, it's a problem that is straightforward, simple to solve numerically using Monte Carlo method, using random number generators. And it's another sort of classic example of Monte Carlo methods. So that's the plan for today. So far in our work with random numbers, we've generated sequences of random integers. We did that, for example, when we were throwing dice. We've also generated sequences of floating point numbers from 0 to 1. We did that, for example, in the radioactive decay chain. I'm going to use one more random number function in the NumPy library today. This function allows you to give the function a list, or there's a function argument is a list, and then it will randomly choose elements, randomly choose contents from that list. And so we'll just use that. We don't have to use that, but it's a very convenient one to use for today's class. Okay, so I wanted to show you the sort of most famous example of random walks, which is Brownian motion, most sort of historically famous example of random walks. So I'm going to switch to this video. And on the screen right now, what you're seeing is a kind of bath of water, and in it are pollen grains. And so this is very small, but not at atomic molecular size, particles, grains in a bath of water molecules. And if you look at these pollen grains in a microscope, what you discover is that they move randomly. They kind of zigzag around, they jitter about. And so it was, a couple of 100 years ago that this was realized, that pollen grains in water actually are in motion. And it's not a very long video. This is an example of Brownian motion. And the motion, another famous example of it is cold dust in alcohol. If you look at that under a microscope, you see the cold dust jittering, zigzagging around. Another example is smoke in atmosphere. If you can look carefully at the smoke particles or dust particles, you can see that jittering around, zigzagging around. They're all examples of Brownian motion. Okay, so I got one slide on look because I've given a little bit of history. But one side on sort of the history and importance of Brownian motion. Then I've got a couple of slides coming up on kind of how we understand Brownian motion as random walks. So that motion of the pollen grains in water was first recorded, at least, by a Scottish botanist who was called Robert Brown, so Brownian motion. So he's credited with observing this sort of zigzagging, random, jittery motion of the pollen. He actually observed a number of features of that motion. So one feature was that motion never ceases. So if you put pollen grains in a vessel container of water, then that random motion never ceases. You know, if you put them in there today, you'll see it tomorrow. You'll see it next week. You'll see it next year. And that answered a question related to, well, maybe they're alive and they're moving around because they're alive. Well, they're not moving around because they're alive. Another feature that he observed was that the speed of the pollen grains increases if the temperature is higher, and it decreases as the temperature is lower. So that's an interesting fact about the Brownian motion. And he also observed that the speeds are slower if the pollen grains are larger, and the speeds are faster if the pollen grains are smaller. So some important features about the Brownian motion. It wasn't until Albert Einstein that Brownian motion explanation was put on a sort of firm quantitative footing. So Albert Einstein made a model of a theory of the Brownian motion in which the motion of the pollen grains is due to the collisions with the water molecules. So if you think about this is collisions between what is a kind of more a macroscopic object, the pollen grain, with entirely microscopic, unobservable in a microscope objects, the water molecules. So Einstein sort of built a theory of this motion. It was based on the fact that the idea then that water is, made of atoms or molecules, water molecules. So there are basic building blocks of the water, of the fluid. It was based on the kind of statistical nature and statistical mechanics of heat and of temperature. So a kind of a modern understanding of heat and temperature. And as I say, it was based on the idea that what's going on is collisions between microscopic water molecules that are unobservable and the macroscopic pollen grains, which are observable. So the explanation of it was at the time kind of a convincing demonstration that water and matter are made of atoms and molecules, are made out of very small building blocks. And actually, it led to an estimate of Avogadro's number, the number of atoms or molecules in a certain volume, or equivalently the mass of the water molecules in this case. So it was Einstein's first sort of major paper and first major impact. Okay, so what we're going to try and do is explore the Brownian motion and other random walk motion by our Monte Carlo methods and our generation of sequences of random numbers. So that's going to be our goal. What I'm going to work through in this class is kind of a simpler situation than the pollen grains in water. It's a situation that's kind of akin to just having a coin, repeatedly flipping the coin, and recording the heads and tails. When we get a head, for example, we'll move 1 unit, say, towards the right. And when we get a tail, we'll move 1 unit, say, towards the left. And that will be our random walk. So it's a simple version of the possible motion of the pollen grains. We can just move left and right, and we can just move in fixed units, 1 step left and right on each flip of the coin. So although that's a simple case, many of the features of that simple case are common to features of more complicated random motion. You know, the pollen grains in the water, animals foraging for food in a field, financial status of a gambler, they all have random walks associated with them. They can all be approximated by random walks. In particular, our random walk is in 1 dimension. We can just go left and right, but you can imagine, obviously, random walks on a surface, maybe the surface of the water or the alcohol for the coal dust. So that would be 2 dimensions, or you can imagine random walks in 3 dimensions, like dust particles, smoke particles. You could also imagine random walks where the step size is kind of a fixed amount, or it itself is a variable amount. And you could imagine random walks where the time intervals between the steps is a fixed amount or a variable amount. And you could imagine random walks where the directions, orientations, could be in fixed directions, or it could be in randomly picked directions. So there's lots of room for different variants of random walks. There's also, we're going to look at purely random walks, but you can also imagine biased random walks, where in addition to the random motion, there's a bias, say, to the right over to the left. It would be like a coin that was biased towards heads rather than tails. Okay, so this is the problem that we're going to look at. We're going to flip a coin. If it's heads, we'll move 1 step, say, towards the right or forwards. If it's tails, we're going to move 1 step towards the left or backwards. And then we're going to carry this out many, many times. And the questions that we're going to try and answer is, after a certain number of steps, what's the probability of you being located at a certain distance, at a certain displacement from the origin, from where you started? So that's an interesting question. You're going to sort of have a certain number of random steps, and you know, how likely or unlikely is it to be at this distance or this distance from the origin? That's one question. Another interesting question would be how far on average, if you repeated the procedure many times, how far on average would you be from the origin? We're gonna answer that question. We picked the 1-dimensional random walk with the single step size because this one we can solve both analytically, write down equations for the distribution, as well as solve it with Monte Carlo methods, solve it numerically for the distributions. So that's why I picked this one. Okay, so I'm going to introduce here, where's my mouse gone? Okay, well, I can't seem to highlight anything, but I wanted to highlight that probability function f subscript uppercase n that's a function of lowercase n. So this is this probability distribution that's describing the chance, the probability of being this far or that far from the origin after a certain number of steps. So the subscript, uppercase N, is the number of steps you've taken. And the argument, the lowercase n, is that your displacement from the origin. So it's like you've taken 10 steps and you're asking, how probable, likely is it that I'm at a location 5 steps from the origin? So that's what f of subscript n, argument lowercase n, is. I've written, so just to get used to this, I've written some out by hand, right? Supposing we take no steps. So no steps is uppercase n equals 0. So f subscript 0. We can only still be at the origin. So we've got 100% probability of being at the origin. That's this guy here that I can't highlight anymore. If I take one step, right? If I take one step, well, what are the possible outcomes? So I can either throw a head or a tail. I can either be one step to the right or one step to the left, with equal probabilities for the unbiased coin. And so here there's 2 non-zero probabilities for one step. I could be one step in the negative direction with 50% probability, one step in the positive direction with 50% probability. So that's easy to enumerate. 2 steps is also easy to enumerate, right? If I throw 2 flips of the coin, there are 4 possibilities. I could get 2 heads, I could get 2 tails, or I could get tail and head and tail. If I get 2 heads, I move 2 steps towards the right. There's one outcome that takes me 2 steps towards the right. If I throw 2 tails, I get 2 steps towards the left. So it's one outcome that can take me 2 steps towards the left. And then if I throw a head and a tail, or a tail and a head, then I end up at the origin. I'm still at the origin after the head and the tail, or the tail and the head. And so the probabilities there are these 3 probabilities. These are the 3 non-zero probabilities. I could be 2 steps to the left with 25% chance, 2 steps to the right with 25% chance, or still at the origin with 50% chance. Okay. Well, I won't go through, maybe I just mentioned this one. So here I've enumerated, I don't want to say it all, though. I've enumerated the case of 3 steps. So that's 3 coin flips. There are, you see the pattern of the number of possible combinations. There are then 2 to the power 3, the number of steps, combinations for the sequence of heads and tails. So 2 to the power 3 is 8. So there's 8 different combinations that I could have thrown, and I've enumerated them all down here at the very bottom. And they range from, again, 3 tails to 3 heads. So I can get as far to the left as 3 steps and as far to the right as 3 steps. Far to the right and far to the left with 3 steps is has a probability of 1/8. And then the other locations are either 1 step to the left, 1 step to the right, which I've got a mistake here, actually. This should be 1/8, sorry. It's ending up 1 step to the left or 1 step to the right, which has a probability each of 3/8. And you see the 1/8 plus 3/8 plus 3/8 plus 1/8 will add up to a total probability of 1. So that's the distribution for 3 steps. Okay, I promise I won't work out anymore. Those probabilities, actually, if you, in each of them, for each number of steps, there's a common factor. We saw it in the denominators. It's this number of possible outcomes, which is 2 to the power of the number of steps you took. If you pull out from the probabilities, that common fact. If you multiply the probabilities by that common factor, then those numbers that we just wrote down on the last slide are actually the numbers in Pascal's triangle. So in Pascal's triangle, it follows this pattern here, right? And at the top of the triangle is this one, in the next row to the left and right are ones, and then the third row is this pattern of 1, 2, and 1. This goes on and on like this. This is Pascal's triangle, and these numbers correspond to those possible outcomes for throwing the coin multiple times. In Pascal's triangle, every number corresponds to the sum of the two diagonal numbers above it. So this one here would be the sum of this, there's nothing in here, and this, so this one. This 2 here is the sum of this one and this one. This 3 here is the sum of this one and this 2. So that's the pattern in that's how you form Pascal's triangle. But it does correspond to the outcomes of these coin flips. So that's kind of mildly interesting, I guess. But here's what's more mathematically important to us. The entries in Pascal's triangle, or these number of these different possible outcomes of coin flips, those entries correspond to the binomial coefficients of the binomial expansion of, I've written in this notation here. So imagine in parentheses this quantity b plus c. We raise it to some power, that's our number of steps. The binomial coefficients for this power are if you expand that out, then they correspond to the coefficients of the terms in that expansion. Maybe let me jump down here. So this is the case of four steps for us. In terms of the binomial coefficients and the binomial expansion, we can get the binomial coefficients by expanding this quantity b plus c to the power 4. So we just multiply it out 4 times. And then if you group together the terms, you get this thing here. So there's a b to the power 4 term with a coefficient of 1. There's a c to the power 4 term. Has a coefficient of 1. You can see that. And then there's terms involving b cubed times c. This should be not uppercase here. Not in the suffix here. There's a b squared c squared term, and there's a b times c cubed term. And these coefficients, the 4, the 6, and the 4, are the remaining binomial coefficients. And those are exactly what's in the Pascal's triangle down here for, say, 4 coin tosses. And they're exactly the coefficients that come out of this expansion. So every row in Pascal's triangle are the coefficients of this expansion, and every row in Pascal's triangle are the possible combinations that lead to a certain displacement from the origin. And so that gives us a way, actually, recognizing that is a way of calculating the probability distribution if you know the binomial coefficients. And so the last item here is I wrote down this expression for the binomial coefficients. You've probably seen this before. So n, in my language here, n is for the coin throws. N would be the number of steps. B would be say the number of times I get heads or the number of times I get tails. And then this is the binomial coefficient based on those two numbers, the total number of throws and the total number of heads. And then if I was to divide that by that common factor of 2 to the power n, the number of steps, that will give me the probability of that particular outcome, the number of combinations that have that particular outcome. So I'm not going to go through all this one also, but here I enumerated it now for 5 coin flips. All right, so starting upstairs here, this is the first coin flip. We can get a head or a tail. It's kind of the parent coin flip. Then the next generation, right, you can get heads and tails over here. So these are the 4 possible, these 4 paths to these 4 points are the 4 possible outcomes for 2 coin flips. Here's 3 coin flips where you can have 8 different combinations, 16 different combinations for 4 coin flips, and then finally 2 to the 5 is 32. Here are the enumerated, the 32 different combinations for 5 coin flips. And downstairs here, you have to turn your head at 90 degrees. These over here, for example, this case corresponds to throwing 5 heads. So that would get you a displacement of +5. And that's the only way to get that. Over here is the combination of 5 tails. That will give you a displacement of -5. That's the only way to get that. But you see, for other cases, there's multiple ways of getting a displacement of +3. Here's 2 of them. Here's another one. Multiple ways of getting a displacement of -3. And there's also multiple ways of getting the other possible displacements, which are +1 and -1. And evaluating the binomial coefficients, here I evaluated all the coefficients you need to find out the probability distribution, is a way that you can basically numerically calculate these probabilities. One final comment about this sort of exploration of random walks for different numbers of steps is that no matter how many steps you take, assuming the coin is unbiased, then that if you averaged many outcomes, so you did that experiment many times, the average displacement from the origin would be 0. The average square of the displacement from the origin would be non-zero. So when you take the average displacement, you're going to get displacements to the left and right, and they're going to cancel out. But when you take the average square displacement, because you're squaring the positive and negative numbers, they're not going to cancel out. You'd only get a 0 then if you never moved. The average square displacement, which is this guy here, is just the number of coin flips. So that comes out of that arithmetic of the binomial expansion and the binomial coefficients. But we'll be able to explore these things numerically with Monte Carlo method and with the random number generation.